Okay, thank you very much, Matt.
Sure.
Basically, I come to this meeting sort of as an old timer, as a mechanistic inorganic and organometallic chemistry interested in the reactions of hydrogen and other small molecules with metal complexes and subsequent catalytic chemistry, hydrogenation chemistry, hydrosylation chemistry. But I also learned about parahydrogen in the course of doing this, and I did that more than 30 years ago. It actually goes back probably 35. So I'm going to talk about really three periods in my research group. I'm now retired. The first, from 85 to 92, relates to the initial observations. The second, 93 to 97, is, I'll call it the Duckett era. And that was getting the right person to work on this problem. And you all know Simon Duckett, and you all know the major contributions that he has made. And then the last part of the talk will involve expanding the scope of chemical systems with regard to parahydrogen polarization and mechanistic significance. I will say that the earliest part of the story of parahydrogen was outlined by me in an Accounts of Chemical Research in 1991. And it said parahydrogen-induced polarization, new spin-on reactions with H2. I think the last sentence of that first paragraph is key. It's a story of quality experimentation by my coworkers, persistent testing of hypotheses, which is something we should all do in experimental science, and a fair amount of head scratching by the author, that is me. So let's begin with how we got here into this very interesting and different area. We were looking at the reaction chemistry of rhodium and iridium complexes. And in this particular case, we were looking at a dinuclear rhodium complex, which is shown right here. In fact, its reactions with unsaturated substrates, in this particular deuterostyrene. We found that when we did this hydrogenation in the presence of this complex, we got these very, very unusual resonances for the added hydrogen atoms. We were not sure exactly what was the cause of this. We originally thought it was chemically induced dynamic nuclear polarization. And in chemically induced dynamic nuclear polarization, unusual resonances and intensities and patterns arise from a radical pair reaction that happens first in a solvent cage and then a solvent separated radical pair. And that one of the channels out of this radical pair forms via the singlet, will form AB, and then there will be diffusion and escape products. If A and B are different in this radical pair, then a net effect is seen. And if the two components here are the same, then one sees a multiplet effect. Now, key players that were involved in this: Gerhard Kloss and Kapteyn, Joe Bargon, Ron Lawler, Howard Ward. These were two colleagues of mine when I was first starting my research career at Brown University. In any case, we had gone through this process and observed the multiplet effect, or what would be a multiplet effect. So after a number of studies with regard to the nature of the substrate, we came to the conclusion that we might be dealing with a symmetric radical pair on the metal center. This, by the way, I should tell you, is totally wrong. But it was reported in 1986. The experiments are absolutely right, but the explanation was not. And in fact, how to test that? Well, we found this linear rhodium, trinuclear rhodium catalyst that had been made by Alan Balch. Alan agreed to give us some of this material. We then looked at the reaction of phenylacetylene with hydrogen, and what we observed is shown right here in that first trace. And in fact, symmetric multiplets. And so it couldn't be the nature of kidnap. We needed another explanation for this. And in fact, it was parahydrogen-induced polarization. We had been in touch with Joe Bargan and Ron Lawler. This is 1986 is the year. They had just come back from a conference at which Dan Weidekamp talked about something called Pasadena and involved parahydrogen. So we, in fact, tried that. The first one was done with parahydrogen. The second one was done with a sample that you'll see in a moment. This one was done with normal hydrogen, and this one was done with independently added parahydrogen. So it appeared that it was parahydrogen that was causing this, and we said that this was then parahydrogen-induced polarization. It, of course, caused us to go back right away and find some early facts about parahydrogen and orthohydrogen and how they had been postulated and experimentally demonstrated or observed in the earliest days of quantum mechanics. So we're talking about 1930 or so. Parahydrogen, as you all know, is the nuclear singlet, orthohydrogen, nuclear triplet. Ortho and parahydrogens are really separable by gas chromatography, and parahydrogen is slightly more stable, as all of you know who are attending this conference, with ratio of ortho to para from room temperature about 3:1 to liquid nitrogen temperatures about 50-50, and then to 20 Kelvin. In parahydrogen-induced polarization, it requires pairwise transfer of hydrogen with spins correlated throughout the reaction sequence, and the transferred protons must be magnetically distinct in the product. Our setup was really fairly crude compared to what people are using these days, but we had our NMR sample. This was in a J. Young's tube. We had a Dewar around this, and basically it was kept at liquid nitrogen temperature. Initially, we just had a flask of hydrogen here. Later on, when we found out that it was parahydrogen and how we could generate that, we put in a paramagnetic catalyst down here and kept it in liquid nitrogen temperature. All of this was connected to a vacuum line. We take the sample, remove it, shake it, put it in the NMR, and start looking at things right away. We also looked at parahydrogen addition to oxidative addition reactions to metal complexes. And this I showed here corresponds to an iridium-1 complex that we looked at and the formation of the corresponding iridium-3. I'm going to try and just move something here that I hope doesn't. All right, so we have the iridium-3 dihydride. This would be the spin designation for the two protons, the two hydride ligands in the product, the alpha-alpha, beta-beta states, alpha-beta, and beta-alpha, as you know. The interesting thing that we found out at that time was that the population difference is only about 1 in 10,000 between the alpha-alpha and alpha-beta and beta-alpha states, and then again, one part in 10,000. And we didn't know that before, but that's something that we learned. Okay, now let's see. I'm going to, all right. In Dan Weidekamp's paper, basically it was for reaction with parahydrogen without loss of spin correlation, population inversions can occur. The alpha beta and beta alpha levels, if you're using parahydrogen, will be overpopulated. And this in turn will lead to an enhanced absorption and emission for one of the protons and enhanced absorption and emission for the other. And in fact, if you look at this, you see the beautiful spectrum for the dihydride product. HB is the one that is trans to one of the phosphines. There's a large coupling here. HA is the other. You know full well the nature of the parahydrogen coupling that leads to the enhanced absorption and emission. At that same time, we were looking at can you use this with regard to transfer to other to other elements that are in the complex. So here is the iridium complex and the proton spectrum. If I looked at the NMR of it, and I think I need to get back this. Under parahydrogen alone, this is what we observed, and this was pretty dramatic. Within 2 minutes, we lost that polarization, and that was from the use of parahydrogen. And if we then looked at it using inept as a means of transfer of polarization, we had essentially the same pattern. And so one could explain what we had in terms of, here were the overpopulated levels that were all in the proton or the hydrides. And then you could get some slight energy changes, and then by dipolar relaxation, population transfer occurred. And when the population transfer occurred, you will get the phosphorus resonances to show enhanced emission and absorption and polarization. Whoops, okay. Somehow I am not advancing. I may ask for a little help. Okay. We went to the another catalyst, a ruthenium hydride catalyst, and we found that the ruthenium hydride catalyst also led to the corresponding parahydrogen-induced polarization in the hydrogenation of the deuterostyrene to ethylbenzene. And I should also mention that PHIP was observed in the hydrogenation when we used other catalysts, but different kinds of effects. And in fact, that related to one that Weidekamp had dubbed Altadena as well. So this slide actually just shows some work that Mitch Chin did in 1992, again, another hydrogenation, and how you could use that to determine the rate of reaction. But really, in part, the paper was, after listening to the geographically specific acronyms, Pasadena and Altadena, we desperately wanted another one instead of using hydrogen-induced polarization. And so we came up with rates of catalytic hydrogenation estimated spectroscopically through enhanced resonances. We could measure the rate of reaction, but more importantly, we were able to say it was Rochester. Okay, at this point, I was able to recruit Simon to come to my lab. Simon Duckett had been doing postdoc work with my colleague Bill Jones. He returned to England in the around 1991, and I was able to get him to come back to Rochester to start working on this. And therein really is the beginning of how our studies took off. Simon started by looking at the reaction chemistry of rhodium complexes with parahydrogen. This is one of those early studies in 1993, and he was able to, through careful decoupling experiments, fully decouple phosphorus. He was able to see that one of the hydrides was bound to a single rhodium, but the other hydride was bound to two rhodiums. He was able to also determine that the hydride bound to two rhodiums also had coupling to this carbonyl. And so he was able to identify this to that carbon. He was able to identify this binuclear compound. Simon did some other spectacular work in terms of looking at the oxidative addition chemistry to chlorocarbonyl bistriphenylphosphine and to Wilkinson's catalyst as well, uncovering intermediates that were previously not realized. Our work with Simon continued with some more collaborations, but they also changed to different metal centers, and I'll get to that in a moment. Let me just put up, this is one of the papers that Simon did when he was here, one of the studies, and basically was able to use INEP plus to transfer polarization selectively to the carbon of the iridium product, the sensitivity that he was able to see was remarkable. This is 3 milligrams of sample with labeled C13, CO, or parahydrogen. This is the same sample with just normal hydrogen, so there's nothing there. This is one with naturally abundant C13, CO, and it indicated just a remarkable sensitivity that the system had. After Simon left, we continued some of our collaborations, we always will, but we personally in Rochester started to focus on other metal systems, and this is one of the platinum dihydride systems. In any case, we were able to see the polarization with platinum H2 oxidative addition. So this had to be, we would form a platinum 0 species, it would add the parahydrogen, then you would be able to see this polarization. These are the satellites as well, platinum 195, that one could see. So the signal enhancement was pretty spectacular, and it worked out fairly well. We then went on to back to iridium, but with adding tin bromide to iridium dibromide dicarbonyl, and we got a dynamic mixture depending on how much tin was added to the system. Tin also has some isotopes that are spin active, and in work that was done by Alexei Perman, you could see that in this particular dihydride product, of all the possibilities, you could identify the HA proton and the HB proton in part through the coupling to tin. So you have that. The trans HB shows a much larger coupling to the tin isotopes. Just a couple minutes later, then you have a dazzling array of different hydrides, and this is at higher temperature. So again, we could see this. We did have parahydrogen in the system that allowed us to observe them. One of the interesting effects so far, all of the parahydrogen that we had seen was for two hydrogens that had been added to a metal center. In looking, excuse me, in looking at the formation of an aldehyde, so essentially a hydroformylation reaction, there's only one hydrogen that is transferred. And Alexei observed this with this platinum acyl complex plus parahydrogen. And here you had now parahydrogen added to the system, but only one of the hydrides gets added to the acyl group. And we did see polarization. And it was either in emission or enhanced absorption. A related system of iridium carbonyl with a dicarbonyl with an acyl on it. Also, there was an oxidative addition. And also, we did get the formation of the propionaldehyde. And again, there were some unusual aspects that were observed and remain strange to us. But it's one hydrogen PHIP chemistry that we're able to find. Another, and the final thing I'll talk about was going to early metal systems and looking at see what other elements might show this. And there is some reason to think that in the early metal systems, if you took this bis-cyclopentadienyl or CP star, actually tantalum complex, in which you had an alkylidine and methylidine bound, you could react it with hydrogen and you could get the hydrogenated alkylidine, meaning an alkyl, and two hydrides that would form. There was a mechanistic question whether there was, in fact, a four-center intermediate in which one of the hydrogens is added directly to E, or whether there's oxidative addition after there's transfer of the hydride, and then you have oxidative addition of hydrogen to lead to this particular product. What the PHIP showed without any question is that, in fact, we do proceed via oxidative addition to the metal center. These are the two hydrides for the CP star methyl dihydride. And then one gets elimination of the methane from that. One adds hydrogen again, and you get the trihydride and are able to observe that. So in any case, that takes us into the end of my talk, which was probably in terms of research over in 2005 or so. I want to thank all the people who worked in my lab on this research. Tom Eisenschmidt, Rain Kurz, Mitch Chin, Alexei Perman, Susan Oldham, Mihei Zhang, Dawn Briegel, and Dan Fox. But mostly I really want to acknowledge Simon Duckett for really developing and moving on to create the field that we're talking about today. And it was my good fortune to be able to help him on that path. With that, I thank you very much.
Rich, thank you so much. This was an absolutely incredible talk and a nice slice of really only some of the work. As you point out, this ends in 2005, some of the work you've been doing in your group. So thank you so much for sharing with us. If there are questions from folks, please type them in the Q&A. There's one from John Blanchard already asking about that platinum compound. And he says, is that platinum compound chiral by any chance? And are you aware of any chiral complexes with heavy atoms that can be prepared with enhanced polarization via PHIP?
Yeah, it's an interesting question. No, the platinum compound is square planar, so or it's planar geometry. I don't know the conformation of the, because we didn't do a structural study of that chelate ring. but my feeling is that it would not be chiral. Now, can you have chirality? The answer is yes. And I think that some of the tantalum, there's a bis CP tantalum derivative that in fact you could create chirality on that with a strap between the two CP star ligands or CP cyclopentadienyl ligands. So I think you could create it. Did we look at it? The other is with the diphos, of course, and we did not look at polarization involving the iridium diphos compounds or the corresponding rhodium ones.
Great. We have a question, a very interesting question from Malcolm, a little bit about the history, saying, I wonder if you could say anything about the timeline of your and Dan's discoveries. Did he know of your observations when advancing the parahydrogen mechanism?
Did he know? Yes. When it was, I think he was working independently at Caltech. Another person at Caltech at the time who interacted with Dan was Jay Labinger. And I had been in touch with Jay Labinger in terms of informal discussions and stuff. But prior to the Pasadena paper, I don't think we were in touch. When I heard from Bargon and Lawler that parahydrogen effects were being reported, I did get in touch with Dan about that. I had hoped at one point that we would be able to publish the experimental observations together, but we didn't.
Thank you for that. There's a question from Boyd. Are there any differences in tantalum chemistry that might offer some new avenues for PHIP that haven't been explored as well with other commonly used metals?
Yeah, actually, it could be. It could be. Our efforts there were relatively limited, and I think it has possibilities. But this was done by one person, and Dawn Briegel, and there's some additional work that she did that I did not mention, and there may be aspects there too. But there are also mechanistic questions in the early metal chemistry, and it is possible that parahydrogen could be used and polarization transfer could be used to study those.
Do you have any tips for approaching ways to assign resonances in complex hydride regions of the spectra?
Well, obviously, right. You start to look at the, you look at the couplings, you look at the hydride resonances. I would go back to the paper that Simon and I did together in probably 1991 or two. And there he really teased apart different phosphorus resonances or different the effect of different phosphine donors on the pattern. So he did a selective depolarization of one of the phosphines there. So I think if you're into that kind of aspect of hydride polarization, and you really are looking for detail there, it could be done. Certainly, I think in platinum chemistry, it could be done.
Here's a question from Allison, and I'm going to clearly distinguish myself as a physicist and not a chemist in butchering what she says here. She says, thanks for all the great work, Rich. Do you think your tantalum-3 oxidative addition relates to more, now here's where I get in trouble, alkylidine chemistry in the wider field, or is this special to H2?
Yeah, well, there is a whole aspect of this where people were talking about something called sigma bond metathesis. And instead of having an oxidative addition to a metal center and then the transfer of one of the ligands to another ligand on the metal, there would be a concerted four-center reaction. And that's what one of the questions that we were interested in looking at. From what we were able to see, it didn't look like there was that sigma bond metathesis. But then again, we were dealing with one of the ligands which was attached to tantalum that had a double bond, if you will, formally. So I wasn't looking exactly at the sigma bond metathesis model. At least that's what, so do I think it could exist? Yes. Has it really been demonstrated the way I would go to people's work like Don Tilley at Berkeley and examine that most carefully.